Now we're going to talk about collisions. There can be a lot of really complicated collisions. We're going to start simple and just think about two masses. When two masses interact impulsively, and you know what that means now, big force, short time, and they exchange momentum. We're going to illustrate all of our simple two-body collisions here with these cars. They're fairly frictionless, so we don't have to worry about friction too much, and we'll look at what happens when they crash into each other. Okay. Now to get started, we really want to start even simpler than that. Let's start by saying we have two identical masses. So same mass. So here they are. Here's one with mass m, and here's another with mass m. Identical. One approaches at vi, the initial velocity. So there we go. That one's moving at vi, right? And the other one is still. One approaches at vi, other is still. It is not moving like that. And the question is, after they interact impulsively, what is going to happen? We don't know. How are they going to move? So the question is, what happens? That's the exciting part. I don't know what's going to happen. One thing I do know is they're going to conserve momentum. That's the one thing I know for sure. So let's see how you could conserve momentum here. So we're going to do it mathematically later. Now let's just think our way through it. The initial momentum was m times vi. So one way you could conserve momentum is you could have this one stop and this one go at vi. Right? That would conserve momentum. But there's other things that could happen and still conserve momentum. You could have this one move forward at vi over 2, and this one could move forward at vi over 2. Right? No reason that couldn't happen. This one could move forward at vi over 4, as long as this one moves forward at 3/4 vi. Because then it's still going to be m times v over 4 plus m times 3 v over 4 is m times 4 v over 4, which is mvi. So the momentum would still be conserved. You could even have this one bounce backwards at 2 vi, as long as this one bounces forwards at 3 vi. Because then the final momentum would be m times vi. So as you can see, conserving momentum is important, but it's not enough. We need more information to decide which one of these is going to make it happen. In the previous board, we found that conservation of momentum isn't quite enough. We could think of a lot of scenarios when two things collide that would conserve momentum, and only one scenario is going to happen. Right? The universe is deterministic at this scale. There's only one thing's going to happen. So clearly, we need more information. We also need conservation of energy. Conserve energy. And in these little collisions, we only have kinetic energy. We don't really have any mechanism for potential energy. So I'll say also conserve kinetic energy. All right. If this wordy thing bothers you, you could also say that in the previous board, we had a system of one equation and two unknowns. So we need another equation. So we're going to get it here. So you really can't solve these just by conserving momentum. You have to conserve energy. So if we throw that in, it actually leads to three kinds of problems, three kinds of collisions. And rather than just starting to solve them, I just wanted to lay them out and let you understand the differences. So let's start with an elastic collision. So elastic basically means you conserve kinetic energy. Kinetic energy. So you might think, well, what else could there possibly be? That's what we said we have to do. We have to conserve kinetic energy. So in this problem, you know, you have m going to hit another m, and you're wondering what they're going to do, right? So one thing we know is the final momentum equals the initial momentum. But now, the other thing we know is that the final kinetic energy equals the initial kinetic energy. So now we have two equations, two unknowns. That seems promising. Another kind of problem is an inelastic collision. Well, let's see. In an inelastic collision, you lose some kinetic energy. Some K kinetic energy. And of course, you still conserve momentum. So P final equals P initial. But then in a problem, you'll be given how much kinetic energy you lose, right? So you might say, so for example, I might say in this collision you lost 20% of your kinetic energy. So say K final equals 0.8 K initial. And it would probably be some numerical problem with some plug and chug, and you would get to the bottom of it. So that's an elastic and inelastic collision. You have to be careful when you say this. If you say inelastic collision, does that mean an inelastic collision, or you know what I mean? So that is an inelastic collision. So then you'd say, what else could there possibly be? Well, there's one more. All right, there is a perfectly inelastic collision. Okay, perfectly inelastic collision. And what it is, really deep down, it is the most K you can lose and still conserve P. All right. So you might say, I could have an entirely inelastic collision. You have to lose all your kinetic energy. If you lose all your kinetic energy, what's going to happen? Both masses stop. Well, you can't always do that, because if you had initial momentum, that can't happen. It could happen if you had a zero initial momentum. They were coming at each other at the same velocity, same mass, then they could just stop, and you would be perfectly, or you would lose all your inelastic, or all your kinetic energy. But say this one's still and this one's moving this way. It has initial momentum. The final state has to have initial momentum. It can't just stop. There's a limit to how much kinetic energy it can lose. And that's what a perfectly inelastic collision is. It's the most it can lose. So you'd think, wow, that must be hard to calculate. Here's the lucky thing, okay? The lucky thing is it occurs when the masses stick together. Why? Oh, it's complicated. Let's not worry about why. You can actually go through the numbers and convince yourself why. But for now, I just want you to memorize, or just to know that this is the case. Perfectly inelastic, it's the most K you can lose, and it occurs when the masses stick together, which really just means the masses have the same final, the same final velocity. It's another way of saying the two final velocities are equal. So if you look at these three, you might say, what are we going to do first? Which one is the easiest one? You'd probably say, yeah, this is probably easiest, right? And then this is probably second easiest, and then I don't know what the deal is with this. This is weird. It's actually the complete opposite. The easiest one to do is this one. And the reason is, what does this really tell you? Really, this tells you that V1 final, if you were numbering them, equals V2 final. So of the two unknowns, or the two equations, two unknowns you're going to end up with, you're going to have one equation is conservation of momentum. The other one is just this, is that these two velocities are equal. That's actually a lot easier to deal with than conservation of kinetic energy, where the velocities are squared. That causes all kinds of trouble that you're going to see. So we're actually going to go backwards. We're going to do this one first, and then we'll talk about elastic. We're going to start with the perfectly inelastic collision. And recall, that means that they will stick together, so they have Velcro on them. So when I slam one into two, they'll stick together and move as a single object, and therefore be perfectly inelastic. And we're going to start even simpler than that, is M2 is going to be still. We're just going to let M1 crash into M2. So what that means is V2 initial is going to be equal to 0. We're going to dispense with the vector notation for now. We're just going to go sort of vector components. So if it's a positive sign, it's to the right. If it's a negative, it's to the left, okay? So let's see. We would start then like this. So here's M1, and it has V1 initial, and here's M2, and it's just sitting there. And then the question is, in the end, what do we get? We have M1 and M2. How are they moving? Whoops, that's M1, M2. So we know that we can conserve momentum. We know that we have m1 v1 initial. We have zero momentum here for the initial case because it's not moving. So we'll go ahead and say that's equal to m1 v1 final plus m2 v2 final. So we have two unknowns, v1 final, v2 final. We have one equation. We need the other equation. And in the case of a perfectly inelastic collision, you don't really deal with the energy equation. Your second equation comes from this requirement that they're stuck together. Right? If they're stuck together, they move together. So your second equation in this case really is that v1 final equals v2 final. And therefore you can just call it, in this case, let's just call it v final. They're the same. So it's not really the energy, it's the fact that they're stuck together that gives you the second equation. So now we have two equations and two unknowns, and it's pretty straightforward to solve it. This is v final, and this is v final, so it's m1 plus m2 times v final. Solve for v final, just bring the m1 plus m2 under here. So you get v final equals m1 over m1 plus m2. So this factor, this ratio, v initial. So that is the perfectly inelastic collision where m2 starts out at rest. So let's look at that and see if this is how it behaves. So we're going to call this m1, it's the one that's going to be moving, and this is m2, it's going to be still, and I've just got to be able to crash them where they actually stick. So here we go. And let's see, how did that look? It looked to me like it slowed down. And it should slow down. So we started out at some speed, some velocity. This ratio is always going to be less than 1. Say they weigh about the same. This is going to be a half, 1 over 2. V final should be about a half of V initial. It's about what we had. It looked like it slowed down. We could check that though. I could make M2 weigh a lot more. So I can add a kilogram to M2. All right, so now we have a small number over a small number plus a big number. So this should be a small ratio now. And therefore it should go slower. So I'll try to send it in at about the same speed, and we'll see if it slows down even more. Yes, slowed down even more. What if we make this one heavy? Right? Let's see. If we make M1 heavy, then you can see it's still going to slow down, but not by as much. Right? If we make M1 heavy, then it should be close to a factor of 1. Let's see if it slows down. Right, it slowed down, but not by as much. All right, so far, everything is making sense. We have made no wild new physics discoveries yet. But hold on, let's see, maybe we will. So to move forward, we could just make them both move. And it's similar, it's just more complicated looking. All right, we could let them both have velocities. They'll still stick, right? It's still a perfectly inelastic collision. So you still have V1 final equals V2 final equals, we'll just call it V final. And you still have to conserve momentum, right? So now we have M1 V1 initial plus M2 V2 initial. That's the initial momentum. And the final, since they're stuck together, you can just go ahead and write it as M1 plus M2 V final, like that. So if you wanted to solve for this one, well, you just turn it around and you say, what's V final? It is M1 V1 initial plus M2 V2 initial over M1 plus M2. Right? And that's really it. It doesn't get super nice and clean and pretty because a lot of stuff can happen, right? So if we have these two things here, now that I'm letting them both move, well, they could come together, or maybe this one is slow and this one's going to overtake it like that, and then they stick. Of course, it keeps going that way. You could have this one moving slow and this one moving fast, and it will probably end up going the other way. They don't quite stick together. You could also have a perfect balance. What if we had the same mass and they came together at the same rate? Then the momentum would be 0, and if they're going to stick together, they would have to stop. Right? So if M1 equals M2, you could factor out all of these M's, right? And it would cancel, and V1 and V2 are opposite directions with the same amount, you just get 0. It would just stop. So we can see if I can make that happen here. So we bring them together. and they just stop.